Please be reminded that on my channel, because nowadays the internet is very slow, you can look at my channel and just search online MCTE, the same thing, MCTE 521, Robot Motion Planning from last semester. So I didn't upload this time our discussions because it will take time to upload them in the internet. But for now, I will find a time probably at night. But for now, please, if you want to see lecture from the previous semester, it is exactly the same slide, so you can look at them. Okay, now let's continue. Let me share my slide. Okay, share my screen, this screen. So we were somewhere in the this one, just for okay. So previously we have already mentioned, especially in your lab number 1, that the joint values of, for example, for a two-link manipulator. So this is your joint 1, you can call shoulders, and joint 2 your elbow angle. So each of these points corresponds to a posture, an arm posture, just like what is being shown here, that the link will be in a certain kind of posture, or the arm, in this case, the two-link robot will be in some kind of posture depending on what are the values of each joint. So here we say forward because we assigned, we pick a point in the joint and then we draw what is the configuration of the robot or what is the arm posture. So for example, this point of 0, 0, this is that robot, the flat one, where 0 angle of joint 1 and 0 angle of joint 2, it will be just lying down like that. And then we increase joint 2, and then it will sweep like a fan. Yeah, and then increase joint 1, this part here will sweep like a fan, increase joint 2, sweep out like a fan, like that, increase, keep on increasing the joint values. So, but then we say that this one is not a very meaningful motion, because what we need is that we really want to control the hand of the robot, not to control the joint values. Okay, we want to control the other way around. We want to control how the hand moves and then compute the joint values that corresponds to that hand motion, okay, or to that hand position in the workspace. Okay, to do that, okay, we say that this is the forward kinematics that we just have drawn, where you have Q, where Q can be theta 1, theta 2, theta 1 and theta 2, theta 1 only for one joint of a robot or one link robot, and then the hand position of HX and HY. And then if there are 2 inputs, 2 theta 1 and theta 2, you can compute the hand position of HX and HY. So now we go to inverse kinematics, which we have partly discussed from previous meeting, that again, you have to control the hand of the robot, you have a forward kinematics. So the forward kinematics is that one, input of the joint values, and you compute the hand position. So now what we need to do is to take the partial derivative on each side of the equation. So take the partial of x, and then take the partial of f of q. It will be that there is some kind of a matrix from this kind of computation. If you take the partial on both sides of the equation, yeah, you take the partial of x and you take the partial of q. And so it becomes a linear relationship such that there is a Jacobian J that defines the relationship of the partial of x with respect to the partial of q. So this is a matrix. And so if we take the inverse, we take now, because here, if you take the input of delta q, multiplied it with the j, then you take the delta x. That means the small increment movement of the x. So it's still a forward kinematics. So what we want to do is we want to take the value of the delta q, the small increment in delta Q. What is that small increment in delta Q? When you are going to step on the hand movement, a small increment on the hand movement, what is the small increment in the joint values? Yeah. And so to do that, we multiply with the inverse of J, because from here, mathematically, we take the inverse of J to compute for the delta of Q. Yeah. So now we have this inverse kinematics relationship between the small incremental step in the X, in the hand movement, against the small incremental step in the joint movement. So we replace the delta X with some kind of a controller equation. In this case here, it is the incremental delta X will be the small increment or the small values that is related to the error of this desired X against the actual hand position. Okay, A is the actual and D is the desired. So this is the desired X where you want to go. Let me annotate. So for example, okay, this is where you want to go, and your robot is somewhere here. Okay, this is your, I think I have to delete it. I just undo to make it faster. Okay, so here you have your X desired there. Okay, and then you have the hand probably is here. So this is your X actual. Okay, and that error will move. Okay, the robot will move eventually there. Okay, that is caused by the error. So we replace the small incremental step of X, this one, with the error in the desired values of X against the actual values of X multiplied by some gain. Okay, so this is in order for our robot to move towards the desired value, we replace this small incremental movement of X with this control equation. Now, we were able to compute the delta of Q, the small step of Q, maybe here, the delta of Q, the small step of Q at every computational cycle to pull us towards the desired value of X, or the desired value of the hand position. So at every incremental cycle, we provide what is the current value of the Q, add it with the incremental delta Q that we compute from here, and update the Q, and then recompute, update the Q, and then go back here, recompute what is your X of A for the given Q, because you have your X by a forward kinematics of now the new updated Q, and then you compute the X. What is this new X now compared to desired X? So you get a new value of the error, compute it with the delta Q, and now the delta Q again is a step added to your current Q, and then now you have a new value of Q. This new value of Q you input into the forward kinematics, compute the new value of X, and so on. You have to continue this cycle of computation until you reach the error between the X desired against the X actual will be small. Okay, or in some cases you reach the number of iterations. So normally it is this error term, you stop the computational cycle when the error term is less than or equal to 0.1, for example, the sum value, or that is your error term, or the maximum iteration. So we say iteration is greater than probably 1,000. Yeah. So because sometimes if you don't do that and the computation does not converge, that means this error is not achieved, then it will continue on, and then it won't stop computing. So you must have an iteration, maximum iteration computation. Okay, so those two criteria will help you exit the computation, that is the iterative computation. Okay, so let's clear all that. Am I recording? I'm recording, right? Okay, yes. So now let's continue. So I try to rewrite the equation, the slides, so that it will be easily understood based on the value, the variables that we are using. So now we say that this is how we are computing the Jacobian, because we never discussed yet on how this Jacobian is being computed. We just show the mathematical relationship between these variables delta Q and delta X, but we never discussed how J is being computed. So J is being computed, of course, based on this one, the forward kinematics of X is equal to f of Q. And then you take the derivative, you take the derivative as the definition, the derivative of f of Q with respect to Q. Okay, so how is this computed? So from here, of course, we take partial of X is equal to partial of this one, a partial of f of Q with respect to Q, which is this equation here, partial of f of Q with respect to Q times delta Q. So this is the way partial of f of Q with respect to Q is being computed. So how? So the partial of the first component of f of Q. So normally your first component of f of Q here, as we have shown before, is that if there are two output variables, x and y, so x and y, okay, and there are two joints f of, okay, for example, let's just say Q1, because that's what is written here, Q1 and Q2. Okay, so the F1 of Q, the F1 of Q is X. That is the first component of that. This is the first component of f of Q. Okay, and the second component is F2 of Q. Okay, and so on. Maybe Z you have, then that's the third component of f of Q, and so on, until you have maybe here it will be alpha, beta, and gamma. So for the roll, pitch, and yaw. But normally people don't use that. We use the matrix computation. But just for discussion, roll, pitch, and yaw will be, and yaw will be the last three variables. Okay. So this is f of 4 of Q, and f of 5 of Q, and f of 6 of Q. So normally it's up to 6 dimensions, because that is, again, we say position x, y, and z, and rotation x, y, and z around those axes. Okay, so here normally it is around 6, and then the n we don't know. Okay, it could be up to 3 or 2 or 1, 2 or 1, or it could go up to 7, 8 and 9, depending on how redundant your robot is. Okay, so these are the number of joints, and this is the number of x, y, and z, x, y, z, and including the rotation. So it's maximum of 6. So it can go from x, y, and z up to the rotations. Okay, if you say one-dimensional, normally about x. I mean, you're controlling only the x, and two-dimensional, x and y, you are controlling. Okay, so what we are saying here is that the first row, okay, is the delta in the x. This is the delta of f of 1. That means the delta in the x with respect to the delta in the Q1. Okay, so the delta, I mean, this is just the estimates. We are just writing it so that you can see the relationship. Delta in Q1. Okay, in Q2. Okay, so each of these is with respect to Q1, with respect to Q2, with respect to Q3 until Qn. So the first component of the f of Q is delta of x divided by the delta, the rate of change of of Q, in this case, Qn. Okay. So here it says the rate of change of the world, I mean, the motion in the world space divided by the rate of change of the motion in the joint space. Okay. In this case, Q1, Q2 to Qn, depending on the column, but the row will be all in the first component. Here is delta x. Here in the second component will be delta y. Okay, this delta y divided by delta of Q1. Again, this one is delta y, and then this is delta y, and so on. Okay, so if you see the rows is dependent on the x, again, y, and probably if you have a third row here is z. And then the column is dependent on Q1, and second column, Q2, and so on until Qn. Okay, so that's how you take the derivative of each of the element of the Jacobian. Any questions? Okay, if you don't have any, did you understand how each element is being computed? Okay, maybe it's clearer if we give an example. Yeah, so let's move forward. So now, for example, in this case, you have forward kinematics computation of a two-link robot or two joints. How do we know that there are two joints? Again, there are two independent variables, theta 1 and theta 2. Okay, so the output of the hand position, x and y, okay, of course, this is the forward kinematics equation, and the forward kinematics equation is stated like this. And we say this because it is, we use, again, we use the planar robot now because we can easily compute the equations analytically. That's why I choose to compute forward in inverse kinematics first using the planar robot. So once we understand the planar robot, then that's how we start to deal with the much higher dimensional robots from 3 to up to 6, where now we are going to use transformation matrices, rotation and translation. So in this case here, we're not using matrices, we are just using analytical computation. So now, as you remember, is yellow not very clear? Okay, if you remember, we have two links. Okay, and also it moves according to the two joints. So you have L1 here and L2 here, and you have the movement of joint 1, theta 1, and movement of joint 2, theta 2. Okay, that's how we were doing. So the time is coming. So now that's the drawing of theta 1 and theta 2 for the two joints. And so we say that this is of course the x, okay, that part plus the component of L2, which is L2, this component, okay, that component. So this is that component, other one is that component, okay. And then the sine value is this part here, L1 sine, that as that component, you're just adding. And then this one is L2 times, again, the total angle, theta 1 plus theta 2. Okay, that's the total angle. Okay. Okay, sorry. The total angle is this theta 2 plus this theta 1. Yeah. And so you get the sine here. And so that's the. Okay. So that's why we say that we can geometrically compute them. And now we know what is the x. So the total x is this part, okay, which is this. And the total y is this part, which is that, okay. So everything is just in terms of equation. Now, we are going to compute the Jacobian. So how? So we write, yeah, analytically, we say the delta partial of x with respect to theta 1 and partial of x with respect to theta 2. And then the second row is partial of y with respect to theta 1 and partial of y with respect to theta 2. So let me remove all those. So what is a partial of x? So that means that we take the derivative of this. That is the x. with respect to theta 1. Okay, so derivative of x, so the first component, what is this? The derivative is what? So L1 sine, derivative of cosine is sine, right? So minus sine. So here, that's the derivative of the first part. Okay, okay, and then what is this one? Okay, derivative with respect to theta 1. How come it's like this? I think there's something wrong. Okay, there's something wrong. There should be an addition here. Okay, let's take the derivative by ourselves. Okay, there's something wrong here. Typographical error. So partial of L1 with respect to theta 1, so that is minus L1. Okay, sine of theta 1. Let's just say sine of theta 1. Okay, next, derivative of that. So plus, I'm sorry, okay, plus L2, okay, times whatever, okay, whatever is remaining. I mean, sorry, what is this term here? So derivative of the whole term is sine, so minus sine of theta 1 plus theta 2. Okay, multiplied by the delta of theta 1, of course. Okay, that's finished. Okay, that is the first part. This is supposed to be the first part. I think there's a problem when I added them. Okay, this should be together, plus like that and plus like this. Okay, so there's a last term here that's supposed to be, this one is still not there. The last term is the derivative of this with respect to theta 2. So of course this is not there, it's not dependent on theta 2, so that's 0 plus this one. So now L2, then the derivative of that is minus sine, so minus sine of theta 1 plus theta 2. I will correct it later and upload the correction slide in Blackboard. I will take notes, and this is slide 17. Okay, so now, so these are the two terms. So this part here is that part, okay, and this part is that part. Okay, please note the correction. Okay, now, okay, this is not, this is correct. The only one is there's a missing term here. Okay, so now let's go to the next, this one. We compute this row. Okay, delta y with respect to theta 1. So again, this part. So let me change another color, maybe green. So we have this one. You take the partial of y with respect to theta 1. So again, L1, okay, with respect to theta 1, that's cosine of theta 1, okay, delta of theta 1, which is delta of theta 1 with respect to 1, which is 1. So L1 cosine plus L2, then this one is derivative of sine is cosine theta 1 plus theta 2 times partial of theta 1 with respect to theta 1. Okay, that is 1. Okay, so that's the first part, which is this one here is that part. And now, what is partial of 1 with respect to theta 2? So again, I mean partial of y with respect to theta 2. So again, this is y. So you take the partial of this with respect to theta 2. Again, this one is not dependent on theta 2, so that's 0. So here, we take the derivative of that, so that is L2. Derivative of sine is cosine of theta 1 plus theta 2. Okay, times partial of theta 2 with respect to theta 2, which is 1. Okay, so now that is your Jacobian J. Okay, which we can analytically compute. So if there are 3 links, just like what I mentioned in the exercise, so now if there are 3 links, of course, you will just continue. What do you think if there are 3 links? So we remove this. So there's a third term, plus something, plus, okay, what will be the third link? Okay, like that. And then the third link, or maybe, let me, I was very good in drawing when I was young. That's why you can see my drawing. They're really very good. Uh, it shows, yeah, and even until now, I can draw very well. Okay, anyway, nobody appreciates it. Okay, there. So this is theta 1. And here, then this is theta 2. Okay, based on that axis, you'll have theta 3. Okay, like that. So the same thing. Okay, of course, it's not easy to visualize. I mean to compute whether this is the x. You know, you have to minus this, but you don't need to worry because the angles will take care of itself. The signs will take care of itself. So if you add like this L3, so you have L1, L1, L2, and L3. So you have L3 cosine. The same thing, you just continue. Theta 1 plus theta 2 plus theta 3. Okay, so here you just add another term, L3, sine of theta 1 plus theta 2 plus theta 3. Okay, then how do you compute the Jacobian now? Well, you will have a third term, right? Okay, partial of x with respect to theta 1. What is your x? This part here. Yeah. So what will happen? Tell me. What will happen? Okay, let's delete this this part. Now I need to erase so that I can use the rest. This one. I hope I have to do one by one. Okay, let me erase this. Oh, I can erase. I can erase the. Nice. Zoom is nice. I can erase later. I thought I have to click on it one by one. Okay, anyway, there. So now, how should we compute it? Yeah, so equal to, so there are three terms. So we continue. You have minus L1, yeah, sine of theta 1, okay, that this part plus, but because the cosine, the sine, the derivative there is minus sine, so you have L2 sine of theta 1